periodically queries ND's miniport driver for information sending different OIDs. So basically all supported object identifiers will be requested at some point of time, and some of them, especially those that I described on previous slide, are requested quite oftenly. These I/O control vulnerabilities can be exploited remotely even after radio is off. So let's imagine that the attacker injected remotely some exploit code, and then the user turned off the wireless, and then the network management application requested for send an I/O control request for vulnerable object identifier that contains a vulnerability. So the exploit code sent within the frames may get executed. The example of such vulnerability. You can see the code that processes the request for active BSSID info object identifier. It's a proprietary object identifier. So ND's miniport supports this proprietary OID used by management applications to query information about associated WLAN. The driver responds to this OID, returning the information stored in the internal connection structure, supplied remotely within beacon and probe response frames. When handling this object identifier, the driver copies SSID of associated AP access point from internal connection structure into a stack buffer without checking the size of SSID. So it gives us a two-step exploitation. First step, inject malformed frames, wireless frames containing the payload remotely. For example, the access point sends its information including SSID free Wi-Fi for all. And then some attacker system injects some malicious shell code inside the SSID element. The wireless driver stores this information in internal connection structure, and then some management application queries for a vulnerable object identifier, BSSID list in this case. Depending on the data the driver received from these two stations. So it requests for this OID, and this driver tries to return this data, free Wi-Fi for all, and this weird SSID. So it allows attacker to exploit the driver remotely, even having the local I/O control vulnerability. So how to identify them? First of all, to identify the I/O control vulnerabilities that are remote, actually, we need to inspect registers and memory pointed to by these registers in the crash dump caused by the device I/O control request for contents of received wireless frames. How to do it automatically? I don't know. I haven't managed to implement it yet, so I do it only manually. That's a challenge. So, and to increase the likelihood of encountering this type of vulnerability, the penetration tester needs to fuzz I/O control codes along with injecting malformed wireless frames. This will increase the likelihood that the vulnerability actually can be triggered during the fuzzing process. So I'll show you the brief demo. I will show you how to exploit local I/O control vulnerability using malformed beacon frame, and I have modified old version of the Intel W29 and N51.sys WLAN driver. I introduced a demo vulnerability we discussed a couple of slides ago, and I used existing BSSID list object identifier instead of proprietary active BSSID info because well, to demonstrate that an attacker doesn't need a local agent to trigger the vulnerability. Let me open. Oops. Sorry about that. I'm not a good editor, video editor, so I apologize for a bad quality of sound and video. Oh, it seems I'm a really bad editor. All right, let's continue the presentation, and I will try to figure out what's happening with my demo that worked 5 minutes ago. After the, if we have time, after the presentation. All right, so I will briefly discuss 2 examples of vulnerabilities we mitigated in Intel Centrino wireless LAN drivers some time ago. The first example is the remote code execution exploit that we analyzed and demonstrated before previous BlackHat USA conference. The description of that exploit is when station was connecting to wireless LAN network, the exploit injected association response frames. I used 40 to 300 frames depending on different conditions, depending on the surrounding access points. In response to association requests framed with the legitimate access point, the exploit used unspecified oversized SSID element within the association response frame. The BSSID had to match access point's MAC address, and the station had to be authenticated. For example, to the open system authentication access point that was actually used. So let's let exploit inject some nopes within the SSID element, and this triggered the bug check driver IRQL not less or equal, and we see that the contents of instruction pointer and base pointer were overwritten by the data specified by the exploit. But then let's try to substitute the fake payload with the demo payload that we discussed earlier during the presentation and inject it. This what happened in the result of using that exploit, and actually the exploit was more complicated than just injecting this demo payload due to many reasons. But I will not discuss them here. So this is the result of exploitation of Intel Centrino, old version of Intel Centrino driver that we mitigated and released an advisory before the BlackHat. I mean previous BlackHat. And the local I/O control vulnerability example. I'm using the proprietary I/O control fuzzer here to send the BSSID list object identifier. In response to this BSSID list object identifier, the wireless LAN driver should return information about the all detected WLANs in an array of and these WLAN BSSIDX structures. The I/O control fuzzer is configured to allocate output buffer of a maximum size so that it doesn't crash and continue testing in case of if driver corrupts heap chunk. It may happen. So after sending this I/O control request with this object identifier, with the length of the output buffer between 12 and 127 bytes, the W29 and N51.sys returned 128 bytes of arbitrary kernel pool. So the user mode application at least can observe kernel pool contents, which isn't good, but not the end goal of the exploitation. If we turn off the option of allocating maximum buffer size and will allocate output buffer of exact size, for example 12 bytes for IO control request, the driver writes 128 bytes into the 12-byte userland buffer and corrupts heap chunk. So the IO control fuzzer ends up in OLI. This is the result of crashing the IO control fuzzer by the driver. But again, it's not the end goal of exploiting the driver, right? The corrupting user mode buffer. So by changing a little bit, changing the state of the driver was accessing addresses outside of its pool allocation and crashed. So I'm continuing discussing this vulnerability in the white paper. So to conclude, the summary of this presentation. Although we focused on the wireless LAN driver examples, any wireless device driver is subject to remote exploitation. The longer the range of the radio technology, more attractive exploitation is. The exploits targeting such nationwide technologies as WWAN, 3G, WiMAX can be really bad for us because they are global and nationwide. So imagine that we can send the same demo payload exploit to the Los Angeles for the moment. Vulnerabilities in the device IO control API can exist in any device driver and is a generic way to exploit kernel. For example, in network drivers, fuzzing ND's OIDs, object identifiers, covers all ND's many port drivers, WLAN, WWAN, WiMAX, Ethernet, Bluetooth, RDA, and so on. And the last is that local IO control vulnerabilities may lead to remote exploits. So we need to they are as dangerous as any other remotely exploitable vulnerability. So as a call to action, blue screens in network drivers are not just functional bugs. We need to analyze every crash dump for a potential security vulnerability. We need to use available tools like on Windows Driver Verifier and ND's test for Windows drivers. We need to fuzz remote and local driver interfaces. We need to integrate automated automated static source code scanning into the development process, for example with prefuzz or any other software static code scanner, and we need to do manual source code analysis. And we also, the drivers, need to leverage the available compiled-in protections like stack canaries and so on. As a final remark, I would like to acknowledge Nathan Bixler from Intel Corporation, and you can you see the contacts. You can contact us regarding any vulnerability exploit or any information about Intel products. All right, this is the final slides. I appreciate your attention, and I still have 10 minutes, I think. Wow. So let me try to launch this demo. Hi everyone. Oops. Thank you. So it is working with the